Thanks. I'll begin with a word of prayer. Dear Heavenly Father, we thank you for this day. I thank you again for these students. Thank you for the break, which we just completed. I hope we're rested and refreshed. I just pray that we'd be able to understand the math we go over today, and that you just continue to encourage students to do good work this semester, Lord. In your name I pray. Amen. Okay, so let me get right to it. Here I could, sorry, taking up half the front row here. So, let's get right to it. First of all, do not despair. I'm pushing your homework back to Wednesday because I won't have time for homework questions today. It'll take me all of today to explain section 12.4 to you. And then tomorrow I'll cover 12.5, and then hopefully we'll have about like 20, 30 minutes at the end for questions. You have a whole lot of homework, something like that. Okay, so root and ratio tests, section 12.4. Here's the first one. Let a sub k be a series with non-negative terms, all right? And suppose the kth root of a sub k goes to rho as k goes to infinity. Here rho is just some constant, all right? Then there are three cases. If the constant rho is less than 1, the series converges. Case 2, if the constant rho works out to be greater than 1, the series diverges. Case 3, if the constant rho is equal to 1, this test is good for nothing. I mean, okay, the book says it's inconclusive. Basically, it's wasted our time, all right? Well, I mean, it gave us a valuable experience in learning new math, if nothing else. But no, I mean, it really didn't accomplish our goal. Our goal, right, is to decide whether or not a given series converges or diverges. And that's the larger story we're telling right now. Before break, we already have covered the geometric series result, the basic comparison test, the limit comparison test. So those are the tools we already have to work with. And of course also the integral test, which gave us our beloved P series. Those are our main results up till now. And what you're going to see today is that both the root and the ratio test logically fall squarely over the result of the geometric series. The geometric series motivates and establishes these results. Let me show you how. So, case 1. Assume that the kth root of a sub k goes to rho, where rho is less than 1. Okay. Well, if you think about that, what that means is that you can choose some mu, some constant mu, which is between rho and 1. Does that make sense? I mean, it should make sense. I mean, if rho is 0.5, you can choose mu is equal to 0.7, whatever. If rho is equal to 0.99, you can choose mu equal to 0.999. You can play this game all day long, right? There's always some number between rho and 1. Okay, so then you can think about this picture here, all right? So what we have is that the kth root of a sub k, the kth term, is tending to rho, right? That means the picture, these green dots are the sequence. It's eventually zooming in on this value rho, right? So if you go past some point, it must be that everything that's a kth root of a sub k is less than mu. Does that make sense? If the sequence is zooming into this red line, it must be below the black line, eventually. Now, before some point, you could have some violations of this, but we don't care because we're interested in the limit. So it's for sufficiently large k that we're interested. Okay. So for k greater than or equal to some k naught, which is this in my picture, you have that a sub k is less than mu to the k. Because if I take this and I take it to the kth power of this inequality, everything here is positive, or at worst 0. So the inequality is preserved under the kth power function. We get a sub k is less than mu to the k. But now we're done because that's the geometric series, which we know converges in this case because our ratio mu is less than 1. So by the basic comparison test, the series converges. All right. Now, I mean, other books, by the way, will call this the direct comparison test. If you look at my old literature, I mean, the abundance of, I've taught this course a bunch of times, right? And if you look at my old material on sequences and series, a lot of times you'll find I don't call it the basic comparison test. I call it the direct comparison test, if you find older solutions I've written, because other books tend to call that test the direct comparison test because it's making a direct comparison. But basic is a good term too, fine, whatever. Now case 2. So the proof of 2 you suppose that you've got a sub k to the 1 over k goes to rho for rho greater than 1. Hence, there exists a mu such that what? Such that 1 is less than mu is less than rho. There's got to be some mu between rho and 1, but on the other side of things, right? Hence, a sub k to the 1 over k has to be what? Has to be greater than mu for k sufficiently large. Now, we could go a couple different ways here. You could just follow my argument for number 1 just verbatim, and it would get us to a direct comparison or a basic comparison test with a divergent geometric series. We could do it that way. Or we could just strike to the heart of the matter, which is that if that's true, what's this mean? This implies that a sub k is greater than mu to the k, right? But mu to the k goes to infinity, right? As k goes to infinity, as mu is greater than 1, right? Therefore, a sub k does not go to 0, since it's something larger than something that's diverging, right? So the kth term in the series does not go to 0. Therefore, the series diverges by kth term test. All right. How can I convince you that this series is good for nothing in case 3? Well, in order to show you that it's good for nothing, I need to show you that in the case that rho equals to 1, you could have either convergence or divergence, right? Our go-to examples for convergence and divergence, if we're just being lazy and hopeful, is the p series. P equals 1, diverges. P equals 2, converges. You can't get much simpler than these series. I mean, you can get simpler, but things that are simpler may not be useful. Or they might. Hey, I'm going to switch up things here a bit. If you don't mind, I kind of wanted that picture. I'll have to work over here for a second for case 3. Actually, I'm going to go back. How about this? The sum k equals 0 to infinity of 1. Right? So a sub k is equal to 1. A sub k to the 1 over k is equal to, you guessed it, 1, right? Which goes to 1, which is equal to rho. This is clearly what? It's divergent, right? So there's a root, which is 1. On the other hand, the sum k equals 1 to infinity of 1 over k squared converges, right? And if you look at 1 over k squared to the 1 over k power, right? In other words, a sub k to the 1 over to the kth root. What is that? Well, that's 1 over k to the 2 over k, which you could rewrite as 1 over k to the 1 over k quantity squared. The reason I do that is because we have already shown back in section 11.4 that k to the 1 over k power goes to 1 as k goes to infinity. Right? K to the 1 over k is infinity to the 0, but we showed that that particular 1, in fact, does converge to 1. So by section 11.4, this converges to 1 over 1 squared, also known as 1. So there you have it. We have rho equals to 1 for both a divergent and a convergent. I have shown you, without a doubt, this test is inconclusive in case 3. We can't judge anything from it. So far, so good? All right. A good example that is a little bit more, let me show you another example over here. This example I like. I think it's a nice example. The sum of 1 over, let's say, the natural log of k to the k power. I said, well, I'm always tempted to write k equals 1 to infinity here, but can you guys tell me why that would be probably a bad idea? Yeah, log of 1 is 0. That's just not a well-defined thing. I mean, so there we go. Now it actually makes sense at least. Okay. I mean, if I put a 1 there, it's a different kind of, you could say it's divergent, but I would just say that it's not even well-defined, all right? It's something else. It's just not a well-thought-out series. Okay, so this, if I look at a sub k, I've got 1 over the natural log of k, parentheses, to the k power. So what's the k through to that? It's just 1 over the natural log of k, right? As k goes to infinity, natural log of k goes to infinity, right? So that goes to what? The denominator's getting huge. So this is like 1 over 0 in the limit. In other words, this is going to 1 over infinity rather. This goes to 0, right? So you've got a root rho equals to 0. So therefore, the series k equals 2 to infinity of 1 over the natural log of k to the k power converges by root test with rho equals to 0, which of course is less than 1. Yep.
We are not, like we don't have to find the sum.
No, well the question is, does the series converge or diverge? The question of what the series converges to, what the actual sum of the series is, that is a more difficult question that we can only answer for a subset of special problems. But we can ascertain the divergence or convergence of a much larger class of problems. And we can also come to, well, we can estimate. I mean, we can figure out how close, you can make a guess, and we could even quantify how far off we are. We will talk more about that. But at the moment, we're just focused on this question of does it converge or diverge. That's just what we're obsessed with at the moment. Yeah. Oh, I can't answer that. I don't know. What's the best test to use for a given formula that's got an exponent in it? I don't know what that means to you. Like, what I'm trying to say is, you as a student say it's got an exponent in it, right? What are possible formulas that have exponents in them? See, I don't know. Right off the top of my head. I agree, I have something to, I do agree with you in the following sense. There's a whole class of examples like this, which are also valid. So like, if I have this, if I have sum over 1 over b to the sub k to the k power, where I need two things. First of all, I need that b sub k is positive, right? if b sub k is 0, I'm in trouble. And if b sub k is negative, well, then we're out of the domain of section 12.4, which is concerned with non-negative series, series with non-negative terms. So I need that. And if I also have that b sub k goes to infinity, well, that's going to do it. See, because then I'll have this a sub k, which is equal to 1 over b sub k to the k, right? As a sub k to the 1 over k power, in fact, is just equal to what? It's 1 over b sub k, right? Which goes to 0, and hence, by the root test, that'll converge. So I kind of want to agree with you. I think that's the heart of what you're saying, is that if I can look at it and it's just like junk that goes to infinity raised to the k power, and if that's in a denominator, root test says that converges. I'm right there with you. Conversely, if it's stuffed to the k power upstairs, then it's going to diverge. Do I need the root test for that? I guess so, but you see, I mean, using the ratio test or the root test, sorry, whatever this ratio test is, in the divergent case is just kind of silly. I mean, in my view, when I think divergent case, I always look at the kth term test. Like, our proof of the divergent case in this is the kth term test, right? So I usually, when I think about convergence, I think about maybe using the root test, but if I'm expecting divergence, I just go straight to the the kth term test. But I don't know. I mean, I guess if you're working out the root test, you think it's convergent, right? You work out the root test, the root works out to be 2. Well, yay, you proved it diverged, right? But after you work out that root is 2, rho is 2, you might be able to like kind of go back to the original problem and just look at it and go, oh, well, duh, of course this diverges by the kth term test. That's my personal feeling about that, is that the kth term test usually will show you divergent things are in fact divergent, right? So that's a good sort of meta example based on the one I just showed you. All right, so that brings us to the ratio test. What is the ratio test? Well, the ratio test says you can look at the ratio of terms in the series and decide whether it converges or diverges. So you have a series, positive terms, all right? Whoa, where's my other laser? Oh. No, just pens. All right, yeah. Sorry, guys. So here we go. If you have the ratio of a sub k plus 1 over a sub k goes to lambda, all right, then you have 3 cases. Case 1, the ratio tends to lambda, which is less than 1, series converges. If the ratio tends to lambda, which is greater than 1, series diverges. And if your ratio tends to 1, guess what? Again, the test is good for nothing. So these tests are very similar. They're not the same. There are examples which the root test doesn't do anything for, and the ratio test dispatches with ease, and vice versa. They are different tools. But the reason that they're both true is the geometric series. So they are disconnected but connected in that sense. Okay. All right, here it is. So suppose a sub k is positive and the ratio tends to 1 for lambda less than 1. All right. Again, I'm going to pick a mu between lambda and the number 1. Why am I going to do that? Because if I do that, then for k sufficiently large, I have that the ratio is less than mu. Again, it's the same picture, just instead of this being the kth root now, we're just looking at it being a sub k plus 1 over a sub k. That's these sequences. So like here's b sub k, all right? So like beyond some point, and y is equal to not lambda now. Okay, great, all right, so whatever. Same picture though. So if you get far enough out, the ratio sequence is zooming in on this lambda, right? Mu is larger than lambda. So it has to be that the sequence is getting away from mu. So mu has to be above the ratio of a sub k plus 1 to a sub k if we're far enough out. But that is still below the number 1, right? So I have this. You guys, you see why it's true? No? Let me review. So do you see, first of all, we're assuming that the ratio goes to lambda. What that means is if you draw a picture of the sequence, it must be zooming in, getting closer and closer and closer to this value lambda, right? I've assumed that mu is a value larger than lambda. So there's like some finite distance between the dotted red line and the dotted black line. So if I go far enough out, it has to eventually be the case that all of the green dots are below the black line because they're getting close to the red line. But that's exactly the same as saying that a sub k plus 1 over a sub k is less than mu. So, but once you know that, you can multiply, remember a sub k is positive, so it doesn't destroy the inequality to multiply it the other side. We get this, right, for all k greater than or equal to k naught. No. Okay, it was just a bird. I'm okay with seeing birds outside windows. It's the people walking around that bother me. Okay, birds are fine, birds are fine. So as you know, I'm easily distracted. All right, here we go. Consider then that we have, in the case k equals to k naught, well, we get this. A sub k naught plus 1 is less than mu times a sub k naught. What happens when you look at k naught plus 2? A sub k naught plus 2 is less than mu times a k naught plus 1, right? But that is less than what? Here, I'll put in an extra step, since I like you guys. Don't tell the earlier section, Jordan. Mu times a sub k naught. So you keep doing this, all right? If you look at the jth iteration of this, if I look at a sub k naught plus j, well, I can show that that's less than mu to the jth power times a sub k naught by just repeatedly applying, you know, going back up this chain. Or if you wanted to prove this carefully, we could prove it by induction. But that's not especially exciting to most of you. I should have done it in the earlier section. There are more math majors down there. Sorry. Oh well, too late. Lost my chance. All right, so anyway, do you guys agree with this? I hope. All right, so once you see that, what you can do is just set k naught plus j to be k, all right? Where I'm assuming, of course, k is greater than k naught or equal to it, which means that j is equal to 0, 1, 2, 3, 4, whatever. So if k is equal to k naught plus j, I can solve for j. That gives me j is equal to k minus k naught, right? So I just plug this in. I said this is equal to k. The j, I'm going to put equal to k minus k naught, right? And so I get that a sub k is less than mu to the k minus k naught times a sub k naught. But then by algebra, I can rewrite that as this constant a sub k naught divided by mu to the k naught power. That's just a number. And then times mu to the k-fold power. I have this inequality for any k larger than or equal to k naught. At which point we just about have it, right? Because we can argue then that the series converges by basic comparison test. See, because I have that a sub k, right, is less than this stuff over here. They're positive terms, right? We assume that. And this one, I can show converges how? Well, this series, I can pull that constant out, a sub k naught over mu to the k naught. That's just a number, right? It's independent of k. This k naught is independent of k, right? K naught is just based on the relation of mu and the assumed lambda, right? there could be a dependence on lambda with the k naught, but not the k. And so there could be a mu dependence, but anyway, so this is independent of k at least, so that's just a number. And then I've got this series built from well, it's a geometric series with ratio mu. But hey, mu is less than 1. That converges. Convergent series times number, convergent. So by a basic comparison test, the series converges. Again, it's really the geometric series that's driving this argument. That's the heart of it. Was there a question? Comment, concern, conundrum?
Do we have to prove it to the test?
Since you asked, yes. Would be An's question. I don't know. Probably not. Don't ask me that question. I do want you to understand this argument. I think with proper poking, it's not an unreasonable test question. If I warn you I was going to ask it, it becomes a more reasonable question, right? You guys did pretty well on the proof question on the test. The sum of the limits. Something like 50% of you at least got that one right. I was very encouraged. So anyway, I digress. Now, how do you prove case 2? I don't want to write it out, but basically the proof that it diverges is the kth term test again. You can easily argue that if lambda is greater than 1, it follows that a sub k does not go to 0 as k goes to infinity. Consequently, it diverges by the kth term test. And then, you know what's going to work for the inconclusive case? You can just look at. So you can try p equals to 1 yields lambda equals to 1, and p equals to 2 yields lambda equals to 1. So p equals to 1 again is the harmonic series. P equals to 2 is the, well, p equals to 2 series, which converges. And you can easily check that the ratio of both of these guys is 1. And yet one of them's convergent, one of them's divergent, so that proves it's inconclusive. Okay? Any questions? Excuse me. Oh. I always get sick over break. I don't know how it happens. So annoying. All right. Here's an example that I like for the ratio test. Here we have the sum k equals 1 to infinity of k to the k over k factorial. Two of our favorite weird new sequences, right? By the way, some of you tried L'Hopital, something like that on the test. But the thing is that k to the k, it's not a power function, and it's not an exponential function. It's both. So its derivative is probably not one you know off the top of your head, right? In fact, if you have to differentiate x to the x, we usually use logarithmic differentiation, and you discover that the formula is some kind of combination of the power rule and the exponential differentiation rule. So, yeah, sorry about that. Fortunately, we don't need any of that stuff here. So I will say this, so you're starting to ask me kind of like generic advice, like which test to use, right? We're starting to think about that. And really, I mean, after the dust settles, we're going to have kth term test, geometric series, p series, basic comparison, limit comparison, root test, ratio test, integral test, and oh yes, and then the alternating series test. Those are 9 distinct tests. And I probably forgot something. Let's say 10 to round it out. I think there might just be 9. How do you decide which one to use, right? Well, you could kind of draw some kind of flow chart and kind of come up with a plan of attack. I mean, if it's geometric, hopefully you can just recognize it as such, right? Geometric is what it is. If it's a p-series, that's kind of the 10th test. Is it a p-series? That's just a class of examples, 1 over k to the p. Right? Those are important examples to be aware of. But I will say this, in thinking about which tests to use, if I see a factorial, I immediately, personally, I gravitate towards the ratio test. In fact, the ratio test is a very powerful test. It's even more important in sections 8.6 through 8.9. But all right, focus. So ratio test is the way to go if you got a factorial, is what I'm trying to tell you. And when you face the factorial, the thing you got to know, right, is that if I have k plus 1 factorial, well, how do I simplify it? That's one thing here. This k plus 1 factorial, right, is the same as k plus 1 times k factorial. These are the same things. Okay, that's essentially the definition of the factorial function was recursively made to be that. The other thing I'm doing here that you might pick up on, and this is a comment, this is not part of the calculation. Why don't I write it this way? Like, isn't a sub k plus 1 over a sub k really this? I mean, if you look at this, right, it's directly this, right? Why don't I write this? Why do I just write this instead? Like, what does that get me? Yeah, it gets me a much smaller expression where I can write the things large enough that I don't make mistakes, right? If you write the expressions correctly, that's one step along the road of getting a correct answer. If you write things incorrectly, even if you're thinking about them correctly, if you just lose it and then come back to the next step, then if you're looking at the paper to guide the next step, then you're going to be wrong, right? So it's important we write correct steps. I know it's kind of a dumb comment, but it's actually sort of the mechanics of how a lot of times we make mistakes, right? I mean, I could tell from my own work whether I was doing a calculation in sort of one continuous sweep or whether I was stepping away from it and coming back to it. If I'm doing it in one continuous sweep, even if I write something wrong in one step, I might still have the right thing in the next step, just because I just wrote it just for the sake of writing it, right? But what's in my mind is something else, and that's why the next step is right even though the last step is wrong, But if you're using the paper to guide the next step, when you write something wrong, you're stuck. Oh well. Anyway, so yes, less writing, and it's just more to the point of what you're going to do algebraically to simplify, right? Then what's my other step here? K plus 1 to the k plus 1. Now, you guys, the things we're always using are these. A, b to the k is a to the k, b to the k, right? A over b to the k. A to the k over b to the k. A to the s to the t power. A to the st. I mean, these are the things we're using over and over and over again. So when I'm trying to simplify things like this, what I'm trying to do is get it to a uniform power so that I can combine, right? So this k plus 1 is not constructive because I've got a k power down here. But to the k plus 1 power, I can just write k plus 1 times k plus 1 to the k, right? Well, that's nice because now, you see, I've got matching powers. See that? So then I have k plus 1 over k to the k. And it just so happens that these k plus 1 factors cancel, right? And the k factorials cancel, or reduce if you like. And so what do we have? Well, we've got k plus 1 over k to the k, which, by the way, simplifies to 1 plus 1 over k to the k. Just a second. And then this, well, that's exactly the exponential function evaluated at 1 by a previous example we did. If we put an x up here, it goes to e to the x. If I put an x here, this would put an x over here. But basically, we have x equals to 1. Or you could look at it as a specific result in section 11.4. It's like section 11.4.6 or something like that. But you can show that 1 plus 1 over k to the k goes to e as k goes to infinity. Again, for section 11.4. Or if you forgot that, you can use L'Hopital's rule on the indeterminate power stuff, right? Like we were doing over there. Oh, we haven't done that yet. Sorry. We haven't done that. We don't know what that is yet. Okay, so what you got? E is bigger than 1, so the ratio is larger than 1. Therefore, this diverges by ratio test with, can't spell, ratio test with lambda equals to e, which is, of course, greater than 1. I like this example a lot. And maybe this is true of both the root and the ratio test example, right? If you have either a convergent or a divergent example, what can you do? You can take the series you're given, and you can look at the reciprocal series. Well, not the reciprocal of the series, but the series formed by adding reciprocals of your given series, like this. If I trade k to the k over k factorial for k factorial over k to the k, that's a new example, right? But almost the same math applies. The ratio is just flipped. The same limit calculation goes through. Just what? Instead of going to e, you go to 1 over e, which is, by the way, less than 1, right? So, hence, again, this series, k equals 1 to infinity of k factorial divided by k to the k converges by ratio test with lambda equals to 1 over e, which is less than 1. Yes, sir? Well, that was me, wasn't it? It's a very interesting question. Man, not quite. I mean, if I had this, we'll soon learn that this is E. But I'm getting ahead of the game. I'm not sure. The trouble is that I don't think so. I mean, the ratio is going to E. So you're saying, intuitively speaking, it's kind of like this is an eventually geometric series. It's sort of asymptotically a geometric series with ratio E. It's a very interesting idea. I never thought of it that way. I like that. I'm not sure what to do with that. I mean, I'm not saying it's wrong, but it's interesting. Okay, so, okay. Exciting medically based family news. All right, so my children have been sick, and now I know why. So, all right. Okay, so moving on. I mean, that's a great intuition, but it's. I mean, I think if we were to apply the ratio test to a geometric series, what would happen if you applied the ratio test to a geometric series? Geometric series is one for which what? A sub k plus 1 divided by a sub k is equal to r, where r is a constant, right? What happens as k goes to infinity? R goes to r, right? So ratio test will reproduce what we know about geometric series. precisely as we know it, right? If r is less than 1, it converges. If r is greater than 1, it diverges. And although in the case of geometric series, if r equals to 1, it diverges. So we're not inconclusive in the geometric series. But that's different, right? It's not that the limit of the ratio is going to a constant, right? Or that the limit exists of the ratio. It's that the ratio is fixed and equal to a constant. That's the difference between the geometric series and this. Okay, so, yes, sir.
For the ratio root test, if you get the third case where or p equals 1, would any other test actually give you a definitive answer?
That's a good question. We'd hope so, right? Now here's an example. I thought, well, I want another example from this section, right? And so I thought I'll just pick one. I'll try to pick one that's even to show you guys so you have other odd ones to work with if you want, whatever. I thought, oh, this one looks interesting. I'll try this one. I just picked this at random. It's not one of your homework problems. Right here, this one. Number 32 of section 11.4. I would remind you the title to section 12.4 is 11. I'm in 12.4. Root and ratio tests. As you can see, it clearly says root and ratio test. So I said, okay, fine. I don't know any better. I'll try it out. And so I was like, all right. So a sub k is natural log of k over k to the 5/4. Calculate the kth root of this thing. Well, that gives me a natural log of k to the 1 over k power divided by k to the 1 over k to the 5/4 power. So this thing in the denominator, well, that clearly goes to 1. Again, by that result that k to the 1 over k goes to 1 as k goes to infinity. We know from section 11.4. Okay, good to know. The numerator, though, is ambiguous because that's infinity to 0. To see what it does, I look at indeterminate power stuff. So the exponential of the log 1 over k, bring the 1 over k down, and that gives me exponential of 1 over k times log k. All right, but log k divided by k by L'Hopital's rule, infinity over infinity, gives me 1 over log k times k, but this is upstairs. I have something that's going to 0 divided by, it's 0. Okay, that thing tends to 0. So the power then tends to the exponential of 0, which is, by the way, 1. So, yay, all this work has shown me the root test does not apply in a conclusive way. So the root test is worthless. Great. And then I'm like, okay, fine. Maybe it's a ratio test problem. Here's the ratio. A sub k plus 1 divided by a sub k. It's that divided by that, that divided by that. So you rewrite this. What you got is k over k plus 1 to the 5/4 power. As k goes to infinity, this thing goes to 1 to the 5/4 power, which is 1. And this you can show also goes to 1 by 1 applications of L'Hopital's rule. Right? L'Hopital's gets you to 1 over k plus 1 divided by 1 over k, which tends to 1. So those both go to 1. So the ratio goes to 1. Oh, man, the ratio test's worthless to us, too. What is this problem doing in section 12.4? That's why this is a good book. If you work the problems at the end of the section, it prepares you for life. Well, for my test. See, because you might argue, this doesn't belong in this section. You don't use root or ratio test to solve this problem. Hey, what's the deal? See, this is actually something simpler. You don't need root or ratio test for this. All you need, direct comparison. See, because this is like what? I mean, here's the thing. Natural log of k, right, is what? It's greater than or equal to 1 for what? Right, so like, if you ignore, so you got what? You've got some k equals to, let's say, I don't know, how about 3? K equals 3 to infinity, right? Natural log of k over k to the 5/4 has to be greater than or equal to the sum k equals 3 to infinity of 1 over k to the 5/4, yeah. As the natural log of k over k to the 5/4 is greater than or equal to 1 over k to the 5/4, right? For k greater than or equal to e, right? Of course, 3 is greater than e, as is 4 and 5 and 6 and 7. So by by the basic comparison test, but this converges. Oh, wait a minute. Oh, that's no help. Oh, man. Dang it. I tricked myself. Oh. So it remains a mystery for now. Curses. I don't know. Now you have exactly as much as the earlier section does on how to solve this problem. I have looked at the answer key, and it was not helpful.
How is the answer key for the even question?
I'm an instructor. I have the even ones too, you know. I mean, I'm not an idiot. You guys have Google, so you probably also have the instructor's solution manual, if I had to guess. Unless this book is unlike every single... Oh, I shouldn't have made this comment. You never thought of Googling the instructor's solution manual? I mean, come on, this is... You know, what's the point? What's the purpose of homework is the deeper question, right? The purpose of homework is to learn the material, right? So I really don't much care. Like I've told you guys, you can work together. You can seek help on the internet. I don't much care where you get help. I want you to learn the material, and so I don't really view homework as a way for you to get points as much as I view it as a necessary step in your learning. And so, you know, come on. Oh, no, not vines. We don't want vines. Stop it. There's a button up here that says vines. I can only assume that. All right, so just a few comments about this thing called a test. All right. A lot of you guys had, oh, oops. A lot of you guys had that part. Well, sorry. I don't know why you put this thing back on. I guess I'm an idiot. All right, that much has been established. So this, a lot of you guys had right. It was good. I was happy. Woohoo. Not so much. I guess you're like, well, he didn't spend much time talking about it. I'm just going to skip it in my study and see what happens. Well, I guess you saw what happens. All right. This. Some of you got this. Yay. A lot of you got this. Very few of you got this. This is disturbing to me. Because, in my view, this one is easier than that one. I mean, but for some reason, you guys, so many of you put 4 lambda here. I do not know why. I do not know why. But that, of course, is not right, because that's not y prime, it's y. All right. Now, that said, there is a big problem in here. There's a significant percentage of you who cannot reliably solve quadratic equations. That is not good. That is not good. Hey, a lot of you, I think most of you got these right. I was very happy with these. This one, like, I mean, I knew when I wrote this problem you were going to L'Hopital it. I was just sad that I was right. Because this is not a L'Hopital problem, folks. This is a squeeze theorem problem. L'Hopitals will not help you here. It will not. I'm sorry. It won't. And so this by squeeze theorem is 0. Part B, you have infinity. There are I think there were 2 students who got this problem right. I don't know, maybe 2. Very few people got that right. Oh, everyone, almost without exception, got this. They're very. You're in a very select group of students if you got this wrong. Sorry, not trying to, but true. Not the kind of select group you want to be in, but a select group nonetheless. This one, a lot of people left blank. That was a homework problem. And I talked about this asymptotic thing in class. You may have noticed I was a little bit excited about it. I should be worried when I get excited about something. And then this is just, A equals to 1. See, okay, so like, if I was more of a conspiracy theorist, I'd be like, all you guys had the same wrong answer. You were working together. There was some kind of group cheating going on during the test. But in fact, I think it's just group carelessness, which is that you have, you have somehow managed to fail to appreciate that minus a minus gives you plus, right? And a moment's thinking would have shown you that putting -1 here is absurd. You want the area to be positive 1. You're saying that minus x times e to the x has area 1 from going from 0 to infinity. That's crazy. You're saying the area under a negative function is positive. You should... you guys, Hey, a lot of you guys got number 10 right. And like I said, at least half the class, I think, got this just spot on. I was very happy. And those of you who got it wrong, I could see some of you were studying, just didn't quite remember. It's fine. Problem 12. One of you told me this problem was fishy. I have written that I caught many fish with this problem, and that is true. Let's see here. Oh, you can cut it. You can cut it off.